So the first problem on the midterm had two curves on a PV diagram, pressure volume diagram. And you were asked to say, what is more likely? Is the top one adiabatic, bottom one isothermal? Is it top one isothermal, bottom one adiabatic, or you really can't say anything? So this is kind of a similar problem to what we did in the practice thing. So it's the idea being here that we look at condition one and see what, there are many ways of solving it. You can also think about dp by dv, the slope, and basically show that the adiabatic curve should have a steeper slope. It all boils down to the key realization that gamma, which is Cp by Cv, the ratio of Cp by Cv is always more than 1 for any gas. You don't have to say gamma is equal to 5 by 3 or 7 by 4, this and that. No, it's not been stated whether it's a diatonic gas or not. Gamma is more than 1. If we have that true, then let's start with the condition A. Let's indulge ourselves and see what happens if A was true. If A was true, we would be able to say that along this curve, the red one, P3 V2 to the power gamma, which is this point, is equal to P1 V1 to the power gamma, which is this point. We have nothing to do with temperature. We are not even invoking it here. And that would lead to, and then this one is isothermal if condition A is true, which means P2 V2 is equal to P1 V1, and we get a ratio for P3 by P2, which says P3 more than P2, which is consistent with what we see from this plot. The only thing this plot is telling us is that both the processes start or end. The arrow has not been drawn, so it's up to you whether you think of it as expansion or compression. I like to think of it as compression, but there is nothing special about it. So this is consistent with the fact that P3 is indeed higher than P2. Now, if you went to B, you would see just the opposite relation. You would see P2 less than P3, which is inconsistent. So given these things, A is true. If you really started assuming on top of this that T1 is equal to, if T1 is equal, if you started assuming things about T1 and T3, which again you can't, this is a PV diagram, then you would get the conclusion C is true. But really what we wanted to see here is that you can think about this feature of gamma being more than 1 and adiabatic curves being steeper. So that was the problem 1. And I will systematically work through all the problems, and this will be posted online also. And there is a recording. So it's, it's like a practice problem. You can now go and see how we work through it. Any questions? Let's not descend into, I wrote this, did you give me points for that? Are you going to give me points for that? That's something you can figure out later. Okay, good. Okay, on that note, let's start our study of thermodynamics. Any questions about anything from last time? We had a pretty funky setup growing up last time. We were trying to show that the Carnot cycle gives zero, has the same efficiency for any substance. So, and to do that, we showed two engines. We started by contradiction. We said, let's imagine there are two engines operating reversibly between the same hot source and the same cold sink. And if we had that, and these two engines had the opposite efficiencies, we could run one of them in the opposite direction. And that led to a contradiction. And I posted a picture on the Slack from Atkins where he describes it in, they describe it in a nice colored picture very nicely. Please look at it. It's posted on Slack. If you don't have Atkins, otherwise just open any version of Atkins and you should be able to read it. So far we have shown, so what are we trying to do here? We are trying to show that delta S, any gas, any cycle, is equal to 0. In other words, we are trying to show that the entropy when integrated along a cycle is equal to 0, or entropy is a state function. So to do this, we had a 3-step process. First was to show that delta S, a perfect gas Carnot cycle, is equal to 0. This one we did. The second one was to show that delta S, any gas Carnot, is equal to 0. This one also we did. It was a kind of a, this proof is the second one is kind of so far the more complicated one. Now we do the third thing, which is to go and actually show the full delta S, any gas, any cycle is equal to 0. To show this, what we are going to show is that any arbitrary cycle in a PV diagram, and in the next homework when it comes out, I would have you think about Carnot cycle on a PT diagram. You can go and try it out yourself. So basically that will be one of the problems from the homework, to try to express the Carnot cycle on a PT diagram and become comfortable with it, to express it on a VT diagram and become comfortable with it. There's things like that. It's quite useful. So any arbitrary cycle, here we are just working with PV because we are just sticking with one for now. Any arbitrary cycle in a PV diagram can be expressed as a sum of Carnot cycles. That's what we are going to prove. And once we prove this, the remaining is obvious. Let's first prove this and then see how it's obvious. So how do we do that? Well, let's draw a PV diagram. Let's draw a PV space in which we will draw our diagram. Let's say this is our PV space. Let's imagine here a tiny Carnot. It's got an isothermal, it's got an adiabat, it's got another isothermal, it's got another adiabat. Okay, a tiny Carnot. Let's imagine another tiny Carnot that lies below it. That one goes like here, then this adiabat, then another isothermal, then another adiabat. Let's imagine a third Carnot, which looks like, so I have here drawn 3 arbitrary Carnots, and the point, and I want you to think about the change in entropy along different paths in these Carnots. So this one has a path over here, this isothermal, it has an adiabat. This one has an isothermal that moves the red. I use different colors just to show that for this one, the isothermal for the red, let's draw arrows just to be careful here. So the red one goes like this because we are talking about paths. So it's important to here to specify the direction. While the blue one goes like this. The green one again goes like this. So something interesting starts to emerge now. If you start to think about the delta S for red plus blue plus green, that is delta S. Actually, let's write, I don't want to put all the subscripts in there. Let's say I think about delta S red along just that one Carnot cycle plus delta S blue plus delta S green, right? These are 3 Carnots, and we have just proved that individually any Carnot, any gas has 0 entropy change, right? Because each one of them is individually 0. This we know. But now if you think about this, something interesting happens. The red one, that you had this curve in the middle, and the blue one, which is this curve in the middle. So this red and this blue over this bit, the red and blue cancel out. Do you see why? Because they are just moving in opposite direction, right? It has to cancel out. This one again cancels out. So this delta S, red plus blue plus green, can also be thought of as the delta S along a bigger path that looks something like this. I have expanded it slightly to go around, but you see what I mean. I hope you see what I mean. It's excluded all the middle parts, and it has kept the adiabats on the side, and it has kept the 2 isothermals on the top and the bottom. And this is our simple idea. Now we can take this intuition and generalize it. The idea being that if you have any arbitrary cycle on a PV diagram, let's say we draw a cycle like this, some arbitrary cycle which starts here and comes back over here. Then we can decompose this into a sum of Carnots by drawing little Carnots like this everywhere. It's almost like, it's like a quilt or a blanket, and you're looking at the little patches that have made up the blanket. That's the type of intuition you can use. Or if you like tilings, this is a set of tilings that you have used to cover up this space. So I can keep drawing lots and lots of Carnots. And of course, along the edge, I will have to make tiny Carnots, but I can do that. And there will be some errors on the edge. Let's not worry about it too much. We are in a PChem class. We are not in a math class. So once we do that, we have the same idea here that the sum of these Carnots will correspond to the, let's draw some over here on at the very top. If you sum up, we know that all of these little Carnot cycles on their own have entropy 0. Net entropy is 0 for each one of them for any gas. This isn't a math class? Yeah, it's not a math class. Oh, you want a math class? We can go down that way, Zach, if you really prefer that. So it's a physical chemistry class. You got physics and chemistry. There's Dorothy Beckett, who many of you might know, teaches biophysical chemistry. I invite you to go and take class if you haven't taken it. There you will be like, it's everything at the same time. I don't think there is a biophysical mathematical chemistry class. Maybe I should teach one of those. It'll be fun. Computational biophysical mathematical chemistry. Yeah, then that will have everything. So the idea being here is that this Carnot, some of these little Carnots that we drew will be able to approximate everything on the edge, just like this, because everything else will cancel out. If you zoom in over here, the isotherm coming from the top Carnot, which goes like this, will cancel out the isotherm from the bottom Carnot, which goes like this. Adiabats don't matter at all. This isotherm will remain, it is not being cancelled. This isotherm will remain, it is not being cancelled. So on and so forth. This isotherm will remain, this isotherm will remain, this isotherm will remain. In other words, any cycle is equal to sum of Carnots by splitting it this way. Or sum of, a simpler way of looking at it, that some of these perimeters along these, some of the perimeter of this curve is equal to sum of Carnots. I'm writing the same thing again, basically. Or delta S along this arbitrary path A is some arbitrary path, arbitrary cycle that I drew in this PV curve, is equal to summation of delta S along a bunch of little Carnots. And each one of them is 0. Therefore, delta S along any arbitrary path A, any arbitrary cycle A is 0. And that completes our proof that S is therefore a state function, because delta S for any gas, for any cycle along a closed path is 0. If you start from this point and you take some path, some cycle to come back to this point again, your entropy is not going to change, irrespective of whatever path you take. You could take a path like this, you could take a path like this, doesn't matter. If you come back to the same path, any cycle that you draw, and cycle doesn't really have to be circular, cycle could also look something like this. This is still a cycle. You can still imagine it. This symbol following Carnot, that's a summation symbol. That's the summation symbol. Is that the one you're talking about, Calista?
I think the one afterward, the delta after Carnot, S along Carnot.
Delta S along Carnot is equal to summation of 0. It's a sum over 0 because each one of them is individually 0.
I think they just meant the S after like Carnot, like it's plural. It's not a symbol.
Oh, Carnot's, yeah.
So there's two deltas.
Yeah, summation of delta S along Carnot's. I don't know how to make plural of Carnot. I'm going to call it Carnot's. Delta S along Carnot. So this, our complicated cycle can be written down as a sum of little tiny Carnots, and each one of them we just showed has delta S 0. Therefore, the whole cycle is 0. The second one that looks like a delta S, you guys are totally analyzing my handwriting, but hopefully you get the point. Okay, any questions? So what have we shown with this exercise? The key point to remember is in our family of state functions, in our steadily growing family of state functions, we have just, with confidence, added a new member. We started with pressure, volume, temperature, which are state variables or state functions. I'm not going to distinguish between them. Then we introduced internal energy U, which is a state function. Then we introduced enthalpy H, which is equal to, anyone remembers? It's U plus PV or U minus PV?
Plus.
Right. You might be like, how can you forget this? But once we go to new state functions, it will start to become, you will have moments of doubt whether it's plus or minus. The way to check that is to check if delta H is equal to delta Q for constant P process. Anytime you forget that, go and check, and you should be able to see that it is plus. Then we introduced S, but S is introduced in two ways. It was introduced as K, L, and W, where W is the number of ways of arranging the system or multiplicity. We didn't go into that definition, the molecular level definition. What we have paid more attention to in this class is that S is defined as the integral. We really define delta S instead of S as the integral of dq reversible by T. And if you look at this definition, it's not obvious at all as to why it should be a state function, because different paths, even different reversible paths, will have different heat given to the system. Yet, if you divide it by temperature and then integrate it, all reversible paths will give you the same entropy change, which is something we demonstrated over here through a fairly convoluted route. There is no easy way to do that. And it's worth to go through this proof again. Even in a normal take in-class examination, I would have never asked you to go and just prove the whole thing with your books closed. And there's no point in me asking you to do it in a take-home exam. What's your point? It's in your notes. But just go through it and make sure that it all clicks. The first part is easy. The first part, this one over here, involved actually doing math in a PV diagram and just seeing that everything sums up to 0. The second one and the third one were more complicated and more abstract, and it's worth taking some time to look at that. So that brings us to entropy being a state function. I want to talk a little bit more about entropy, and then I will spend just a bit of time talking about K, L, and W just to show you what it is. I haven't proved that these two definitions are equivalent. Previous times when I have taught PChem, I would go through that, but that's really math. That's 2 lectures of solid math. I'm not going to do that this time, hooray. And, but it is optional material. If any one of you wants to read it, please send me a note, email or direct message on Slack, and I will give you the notes for that. And you can go through it as to why are these two completely different looking things exactly equivalent. And I will post it on the channel if anyone wants to see. The next thing we are going to talk about is interesting and important. It's called Clausius inequality. So what is this inequality about? So the reason we are going to introduce this inequality is because we have looked at the second law of thermodynamics in a few different ways, right? First, we looked at in the Kelvin way that it is not possible to run an engine whose sole purpose of existence is to take heat from a hot source and completely convert it into work. That's not possible. You must always have a cold sink. Second way, we had the Clausius statement, right? Or which said it is not possible to just take heat from a cold sink and completely transfer it to, heat does not spontaneously flow from a cold sink to a hot source. So let's look at this Kelvin statement, the first one, more carefully. So one way of looking at second law of thermo is to quantify the heat lost to a cold sink, right? And Kelvin statement says, oh, I always, by the end of the semester, I will get confused which statement said that. As long as you remember what the statements are, the name doesn't matter. We can call them Abby statement and Alexa statement. I really don't care. So it's the heat lost to a cold sink is what we are asked to look at, right? And the idea being that it has to be something. It cannot be zero. You have to lose heat to a cold sink. And then the work that can be done by a heat engine is W, and I will use absolute value to just keep things simple, is given exactly by this difference, the heat that you take from the hot source minus the heat that you give out to the cold sink, right? QH minus QC. And then we defined an efficiency, especially in the context of that part 2 of that proof, which was how much work did you get out and how much heat did you did you have to take. And so what second law of thermodynamics tells us, so this is equal to QH minus QC by QH, which is the same as 1 minus QC by QH. So second law of thermodynamics says that QC must be equal to 0. Sorry, QC must be more than 0. It cannot be equal to 0. In other words, W, the amount that you get out of the system, is going to be less than QH. Another way of looking at it is that if you run an engine with the highest possible efficiency that you can attain, eta is equal to 1, as you tend to eta is equal to 1, it means in this equation over here, eta is equal to 1 means the only way that can happen for a fixed QH is that QC tends to 0. In other words, the amount of work that you get out of a system is always going to be bounded by an upper bound. So we can call it as the actual work that you get out of the system. And here, and I'm going to use delta just for differential work. And this is the reversible work that gotten out of the system. So if you are working the system reversibly, you will be upper bounding the work that you can get out of the system. Irreversible processes imply dissipation. You're always losing heat into the cold sink. So for example, let's start with the math and then see it will make sense what we are talking about here. So let's say we have a state A and we want to go from state A to some state B in some space. It's a PV space or a PT space or whatever it is. And in this space, let's say we have two paths. One path is some irreversible path. We call it I. It's not that irreversible paths always have to be wigglier and jigglier. I just drew one, okay? And then there's a second path, which is a reversible path, which is called R. So what can we say about these two paths? The first thing we can say is that du is equal to delta Q plus delta W. This is always true, right? This is going to be true for both our paths, the top one and the bottom one, the reversible as well as the irreversible path. However, for a reversible path, delta Q becomes the same as TdS, right? That is the definition of entropy, that ds is equal to delta Q reversible by temperature. So for a reversible path, we can write down du is equal to TdS plus delta W. So the fun thing now is that du is going to be the same, whether it's a reversible path or an irreversible path. It is only the delta W that is going to need a special subscript to specify whether it is a reversible or an irreversible path. What does that mean? That means that, so here we can write down delta Q actual or some irreversible path and delta W actual or some irreversible. You could also write irreversible, but I want to write actual because actual includes whether it is reversible or irreversible. It is a generalization of both of them. So these two things have to be the same, irrespective of whether you are taking a reversible path or an irreversible path. These two things have to be the same. Why? Because the left-hand side is a state function. So we can write it down in the following way. We can say, actually, let's go to the next page and write it down clearly. I'll start once again. So what we have said is that du is equal to delta Q actual plus delta W actual, and du is equal to TdS plus delta W reversible. And why is this true? Because du reversible is equal to du irreversible is equal to du actual. By this can sometimes confuse. By actual, I mean reversible or irreversible. It could be any of these, right? Okay. So these two things can be equated. This thing is equal to this thing. So let's do that and let's see what we get out of that. So delta Q actual plus delta W actual is equal to TdS plus delta W reversible, right? Or TdS is equal to delta Q actual plus delta W actual minus delta W reversible, or ds is equal to delta Q. What is the subscript on the second? Du reversible. So this is du reversible, this is du irreversible, and I'm calling both of them collectively as du actual. An actual process could be reversible, it could be irreversible, right? So actual is reversible or reversible. You're welcome. So ds is equal to delta Q actual divided by temperature plus 1 over temperature delta W actual. So something interesting is starting to emerge. We knew that we defined ds is equal to delta Q reversible divided by temperature. But suddenly we are starting to see here an expression for ds that might be calculated even from an irreversible process. So if here the process, if actual process is reversible, then delta W actual is equal to delta W reversible, and ds is equal to delta Q reversible by temperature. We restore our definition of second law of entropy, right? If this is true. However, if actual is not equal to reversible, if it is some irreversible process, then we have to look carefully now at the sign of the work done. So we are thinking about work done by the system. What does that mean? Work done by the system. And this is a very good point to remind yourselves of the first law of thermodynamics sign convention. In our first law of thermodynamics, du is equal to delta Q plus delta W. When work is done by the system, when the system is when energy is, this is a, let me write it this way. If energy is leaving system, if energy is leaving the system, do you expect delta W to be positive or negative? Anyone wants to help me? You can, negative. Why, Elizabeth or Salim? Well, that's the convention, right? The internal energy will go down. The system is giving energy out. So that's the point here. And this is confusing. This notion of negative work, it's always, it's just convention, but it matters. So in this case, what it means is the delta W is negative. So we can say that minus delta W reversible is going to be more than equal to minus delta W actual. And let's take a moment to really, this is fairly abstract statement, what I wrote over here. Let's take a moment to think about it. So you said delta W, you said, at least three of you said, that the work done when the energy is leaving the system is going to be negative. So if nothing is being lost to the cold sink, it's going to be very negative. Does that make sense? Let's say you were taking 100 kilojoule from the hot source. Let's say this was your hot source, and you took 100 kilojoule out of this, and nothing was being lost to a cold sink, and you were able to get 100 kilojoule out of it. In this convention, this will mean that delta W is equal to minus 100 kilojoule. But if you were less efficient and you were losing, say, 20 kilojoule to the cold source, then this thing would look like minus 80 kilojoule. Okay, that's the point I'm trying to make here. So this is the reversible work done. This is the actual work done in some process, which is possibly irreversible. You can see that this number is actually smaller than, minus 100 is smaller than minus 80. But the thing here is that the absolute value of minus 100 is larger than the absolute values of minus 80, or negative of minus 100 is larger than negative of minus 80. So minus delta W reversible is more than equal to minus delta W actual. So this is kind of abstract. If you get confused, please tell me on Slack. I can go through over this again next class, or do something like that. So let's number this equation as equation 1, and let's number this equation as equation 2. So if you use 2 in 1, what do you get? You get ds is equal to delta Q actual by temperature plus 1 by T plus something delta W actual minus delta W reversible. What can we say about the sign of this thing? This thing is going to be positive, right? If you take this delta W actual and bring it to the left side, and take this delta W reversible and bring it to the right side, it's a positive number. Or ds is more than equal to delta Q by temperature. This is called Clausius inequality, not to be confused with Santa Claus. And notice I have removed reversible, irreversible, actual, everything out of it. Why? Because if it is a reversible process, then ds becomes delta Q reversible by temperature. If it is an irreversible process, the entropy change will always be more than the heat given to the system. So this is a super, super important relation. I cannot emphasize how important this is, because the next 3-4 weeks 5 weeks, 6 weeks, maybe as much time as we have in this semester, are kind of built around this relation. Electrochemistry is built around this relation. Phase diagrams are built around this relation. Chemical equilibrium is built around this relation, because all the things that we do next will follow from this little thing. So we just said that ds is more than equal to delta Q by T as Clausius inequality. The reason this is very interesting and important is because of this S. This S here is entropy of system. It is not the entropy of the universe. That's what makes it very powerful. When you are designing, I don't know how many of you attended Stan Whittingham's lecture yesterday in the Tobin Marx lecture in chemistry. He's the Nobel laureate in chemistry from last year for inventing lithium-ion battery. If he had not invented lithium-ion battery, life during pandemic would have been very different, because every single device that we are using right now is running on a lithium-ion battery. And his talk was, as you probably noticed, was a lot of thermodynamics, kinetics, but also a lot of thermodynamics. And and in order to study any of the systems, for example, he made, it's hard to talk about the entropy change of the universe. How do you know? In a model system, maybe you can talk about it, but in an actual system, how do you go about and calculate the entropy change of the universe? Oh, I will explain that, Elizabeth. Just give me a moment. So the nice thing here is this entropy is the entropy of the system. So the idea being here, to answer Elizabeth's question, is that ds is equal to delta Q reversible by temperature. ds is more than equal to delta Q irreversible by temperature, okay? Because if it's an irreversible process, then this thing in the square bracket is going to be positive. Michaela has a nice question. Was the second path that ended up at minus 80 kilojoule irreversible or actual? It was both, Michaela. It was irreversible. So what we can say there, it is not a reversible path. How can we say that it is not a reversible path? Because we know that there is another one which was able to get minus 100 kilojoule out. We know there is more bang for the buck possible. So it's definitely not reversible. So I know this thing confuses. So actual, any of these could be an actual path. Actual could be reversible, actual could be irreversible. It's just nomenclature. I know I'm maybe making your life harder, but trust me, it gets more, I've tried other ways and it gets only more complicated. So these two things together are summed as ds more than equal to delta Q by T, where if it is irreversible, you will be using the inequality, and if it is reversible, you will be using the equality. That's the idea, okay? Actually, I can write it down as this way. If it is an irreversible path, it's definitely more than delta Q irreversible by temperature, okay? Because the thing is positive. I'm not saying this thing is more than equal to 0 for irreversible path. This thing over here is positive for an irreversible path. So, and I want to emphasize, this is entropy of the system. This is wonderful. You remember when I was trying to bash creationists for using second law of thermodynamics to disprove evolution, I said, well, you're talking about the entropy change of the system plus surrounding. You can't say anything. This is a generalization of that. This is entropy change only for the system. Indeed, if you have a closed system, what can we say about a closed system? What will happen to delta Q for a closed system? It will be 0. For a closed system, delta Q is equal to 0. Therefore, ds is more than equal to 0. And we recover our third statement of, second law of thermodynamics, right? So the point being here is, if you have a system embedded in some surrounding, and let's say the surrounding, system plus surrounding make our known universe. There is nothing that we care outside it, or in other words, they are thermally insulated. This thing that we wrote applied to ds system plus ds surrounding, while this thing that we wrote, or this thing that we wrote, is only ds system. And that's what makes it so useful. The reason I say this is very, very important is, once again, because this is only entropy change for a system. That is something we can calculate. It's easier. And next class, we will start to talk, next class, or maybe the class after that, we will start to talk about these things called Helmholtz energy and Gibbs energy. They are just a restatement of this thing in constant volume or constant pressure conditions. So it's important to drive this home, this Clausius inequality. And it's a kind of a subtle argument. It's easy to get confused because the heart of this proof was this realization that delta U is the same for reversible path or for irreversible paths. It doesn't matter. So any questions about any of this? Some of you emailed me that you feel shy in asking questions on Slack or on Zoom chat. I hear you. I want to comment two things on it. It's always hard to ask questions in a classroom. If you think it's hard to ask questions here, raising your hand and asking a question in one of those big auditoriums is even harder. So it is hard, I know. I mean, sometimes in seminars, I feel stupid while asking questions. But in fact, I have a funny story about it. When I went to grad school, it was at a school where the undergrads are particularly obnoxious. It's called Caltech, and they are really, really strange, the undergrads over there. I mean, I cannot say anything. So I was in my quantum mechanics graduate class, and I asked something, I raised a hand, and one of the undergrads actually laughed at me from the back for asking that question. It was terrible. So you guys at least don't do that. So please don't feel shy in asking questions. Those are some terrible undergrads over there, very judgy. But if you still feel shy, send me a direct message, and I can post your question anonymously on the channel for people to discuss or to have a discussion. I don't know how you will post the question anonymously to me as well, and maybe that's not even a good idea. Even if I was using Piazza, I wouldn't have that setting on. So I would like to know who you are, but if you don't want others to know who you are, use the direct message feature on Slack or just email me, and I will post the question anonymously on Slack for everyone to discuss. So this is Clausius inequality. Next time we are going to look at something slightly practical, which is how to measure entropy. And how does it change in the core as a function of temperature? How does it change during physical process such as sublimation or something like that? It's useful. It's not hard. It's much easier than the things we have done so far, but we will do it. What is the entropy for vaporization and things like that? Once we do that, I think it will take maybe 15-20 minutes. We will come back to this Clausius inequality, and we will use this to talk about spontaneity and free energies. So next time we will start. So next class, we will talk about measuring entropy, which has a nice section in Atkins on that. And after that, we will begin our discussion of spontaneity and free energies. And we should have the midterms released by following Monday. It's frozen, but I haven't written anything profound. So let me do it again. I was just writing what I will be doing next time. So I was saying what the two things that we'll do next time. And this is the main thing that we will start in next class, spontaneity and free energies. And after this, we will get to everyone's favorite, Maxwell relations. And from there, what do we do next? We will go to things called phase diagrams, electrochemistry, chemical equilibrium, and time permitting, we will do chemical kinetics. There is a joke there. I don't know if you got it or not, because kinetics is the study of time, you know, time permitting, we'll do that. So this is really a map, more or less, for the remaining of the semester. The abstract ideas will kind of start to end around here, around Maxwell relations. This starts to be more practical, but for some students, this can be quite complicated. And it's a lot of material, but you know, thermo is a dense class, PChem is a dense class. You will be using this material in a variety of different frameworks, and it's a lot of material. And okay, I don't want to do anything new. I just wanted to tell you about the second midterm. So the second midterm will happen in the first or second week of November. It will be a different format. It will be a choice. It will be a presentation-based format. You will either be making presentation on a research paper, or you will be working on an actual project or an actual problem. You will be working in teams of 5, I think, and we will figure out how to divide everyone into teams. You will have a choice of maybe 4 or 5 papers. 2 of the papers will be biochemistry oriented. For example, there is a classic paper that I have in mind where all these ideas are used to figure out how hydrophobic is a protein. And it's basically all about heat capacity measurements and things like that. It's a classic paper in biochemistry. And you will be able to understand that. One paper will be about battery materials, looking at all of this in the context of battery. There will be some more theoretical papers. And for those of you who are like computer programming, instead of papers, I will have an actual project where you can go and do calculations and put these things in practice. So you will have at least 2 weeks to work over this. You will be in teams of 5. Every member of the team will submit their own individual report, but one member from the team of 5 will be making a presentation, and we will go through that in detail. So that will be the format. I will be grading very leniently on that, conditional on you putting in the work. So, and it will be a different experience. Last 481, when I thought I did this, and the students seem to have liked it a lot. And I hope you will also like it. It's a lot of fun. We'll have to figure out how to divide teams, and we will get to that. The final will be similar to the midterm. It will be take home. It will be slightly longer. And I don't know what the final date. It will not be in November. It will be after first week of December. So somewhere around 5 to 15 December, roughly. But this second midterm, I will release the papers and the problems. You will get at least 3 weeks to work on it. You can work on it gradually as a team. Okay, any questions about this? Will we have several days to take the final? Oh yeah, you will have more time. You will have at least 7 days. But do you really want 7 days? I was thinking this time that maybe I should just give you 1 day, because it seems like no one seems to have taken only 2 hours. If you get more time, you tend to spend more time, right? Several days would be nice. Okay. I will give you at least a week. Don't worry. It will be at least 1 full week. Is that fair? It will be, let me not be a politician and make promises I cannot fulfill, but I will try it that it is a Friday to Sunday, following Sunday, you know? So it's released on, it will be open note, open discussion, 1 month, full send. Nah, I'm not giving you 1 month. That's not happening. Okay, on that degenerate note, I'll see you Friday, and we will have office hours following Monday. Okay.